Hi everyone, my name is Zhiyang. Today I'll be presenting the paper Breaking the N to the K Barrier for Minimum K Cuts on Simple Graph. This is joint work with Jason Lee. Now the minimum K cut problem is a very well-studied problem, so we'll quickly review the setup. We have an undirected, unweighted simple graph G and an integer K, and we want to find lambda K, which is the minimum number of edges to delete to cut the graph into at least K components. Now, in our case, we'll be thinking of K as a growing parameter. So in particular, we're going to ignore n to the O of 1 factors in our runtime. Okay. So since this problem is so well studied, there are a few important results that we need to cite. The first result that we cite is the Karger-Steins randomized contraction algorithm from 1996, which runs in time roughly n to the 2k. Again, we're going to ignore n to the O of 1 factors in the runtime. And the next result we cite is a deterministic algorithm by Sorup from 2008, which runs in time n to the 2k as well. And the third result is a breakthrough result by Gupta, Harris, Lee, and Lee from 2021, which shows that perhaps surprisingly, the original Karger-Stein algorithm runs in time n to the k. And there are a couple points about this result that is quite amazing. And in fact, we'll be citing the result twice in our paper. But a few points to note here is that the Karger-Stein algorithm works for weighted graphs. And they also showed a reduction from the minimum K cut problem to the max weight K clique problem. So assuming the complexity conjecture that the max weight K clique problem cannot be solved faster than n to the k, the runtime of the Karger-Stein algorithm is actually optimal, up to polynomial factors. Okay. However, for the unweighted case, the conjecture lower bound is only n to the omega k over 3. However, the best algorithm we know for now is the GHLL analysis of the Karger-Stein algorithm, which runs in time n to the k. So the goal of this paper is to partially address this gap. In fact, the main result that we're going to show is as follows. It says that there's an absolute constant epsilon such that the minimum K cut problem can be solved in n to the 1 minus epsilon K time. And in fact, we're going to give evidence that n to the omega K over 3 may indeed be the right answer, assuming that K clique cannot be solved any faster on simple graphs. Okay. So before we get to our main algorithm, let us try to lay down some motivation and intuition. We're going to introduce the most important technical component used in our proof, namely the Kawarabayashi-Sorup graph sparsification algorithm from 2018. Now, the sparsification procedure roughly says the following. Given a simple graph G with minimum cut value lambda, it's going to return a partition of the vertices such that if we contract each part Vi into a single vertex, which means we're going to remove all the edges within each part, and the resulting graph will be a multigraph, then all non-trivial min cuts of G are preserved in the resulting graph H. Here, non-trivial means that both sides of the cut have more than one vertex. So in particular, if one side has only a single vertex, we're going to call it a singleton side. Okay? And moreover, the resulting graph will have roughly m over delta edges, where delta is the minimum degree in G. So this is a really amazing result, and we're going to see it in a short moment, how we're going to apply it. But a couple of remarks to make is that the original procedure is actually quite complicated. It is simplified by Saranurok using expander decomposition, and it's also generalized to K cuts instead of just 2 cuts by Jason Lee. Okay? So now let's quickly motivate our main algorithm by considering the case where K equals to 2, so just regular min cuts. We'll briefly discuss Saranurok's deterministic algorithm for min cuts, and in particular, we'll make use of a lemma by Gabal, which is a parameterized algorithm for min cuts. Okay, so the lemma states that there's an algorithm that given G and a parameter K, it's going to return the minimum between lambda and K. Here, lambda is the min cut value of G in time O of the minimum times the number of edges M. Okay, so now we can very simply combine this lemma and the KT sparsification procedure to get an algorithm for min cut as follows. we first run the KT specification to obtain the graph H, and then we run Gabel's algorithm on H with parameter delta, which is the minimum degree of G. So now there's two possible cases, right? If G has a trivial min cut or a singleton cut, then Gabel's algorithm will return delta, in which case we can just look into all the vertices in G and find the minimum degree one, and that will give us the cut, right? But what if all the minimum cuts are non-trivial? Then Gabel's, even though it doesn't state it right here in the lemma, Gabel's algorithm will return a min cut in H, which will be a min cut in G, because by the guarantee of the KT sparsification procedure, all non-trivial min cuts are preserved in H. Okay, so this is a very simple and elegant algorithm for min cuts, and our main algorithm is going to follow a similar spirit. Okay, so the real result that we show in this paper is as follows. Suppose there exists an algorithm that takes in a simple unweighted graph G and returns its minimum K cut in time lambda K to the TK times some polynomial factor for some constant T. So in particular, we're looking for a parameterized algorithm. Let the constant C be the maximum between T over T plus 1 and omega over 3. Then we can compute a minimum K cut of a simple unweighted graph G in time n to the CK. Okay, so a couple of remarks we need to make about this result. Does such a parameterized algorithm exist? Yes, actually. Recently, there's a result by Lokhshtanov, Sarab, and Syrianarian that showed an algorithm for exact minimum K cut that runs in time lambda to the O of K times some polynomial factor. So combining their result with our theorem, we get the promised result of an n to the 1 minus epsilon K algorithm for computing minimum K cuts in simple graphs. The next remark we want to make is that we use this parameterized algorithm in a complete black box manner. Okay, so as we mentioned before, our result shows partial evidence that n to the omega K over 3 might actually be the right answer. And as follows. If one can improve the parameterized algorithm runtime to say lambda K to the 2K or T equals to 2, then our overall runtime will be n to the omega K over 3. Okay, so this is what we mean by partial evidence. Now let's see our actual algorithm. The first technical component, as we mentioned before, is going to be the KT sparsification procedure. And we're going to cite the sparsification procedure for K-cuts, and the statement is roughly as follows. So again, given a simple graph as before, we're going to compute a partition such that if we contract each VI into a single vertex, all non-trivial minimum K-cuts are preserved in H. And moreover, H has n to the n over lambda K vertices. This bound on the number of vertices is actually quite important, as we'll see in a moment. But this is the KT sparsification for K-cuts. Now, this sparsification procedure and the parameterized algorithm by LSS enable us to do the following algorithm. Okay, so the start of our main algorithm is as follows. We're going to start by running an approximate K-cut algorithm to get an estimate on lambda K. Okay, now if lambda K is small, which means it is at most n to the 1 over T plus 1, then we can run the exact algorithm by LSS, and the overall runtime will be n to the TK over T plus 1. And that's great, because that's exactly what we promised. If lambda K is large, then we can apply the KT sparsification procedure and get the graph H on n to the T over T plus 1 vertices. Because recall earlier, H has n over lambda K vertices. So in particular, when lambda K is large, the resulting graph we get is much smaller, which is great because now we can apply, say, some well-known results like Karger-Stein. So if G has non-trivial min cut, then it is preserved in H, which means we can run the Karger-Stein algorithm in time n to the TK over T plus 1. And we'll get a min cut for G, and that's exactly as we promised. So the remaining case, which is the difficult case, is what if all the minimum K cuts are trivial, which means they have either one or many singleton sides, right? So this is our main contribution. So we proposed an hopefully intuitive solution to this case. And to start thinking about it, we need to look into how does this KT specification does to these K-cuts? Like how do they operate on these K-cuts? Does it hopefully preserve them? Does it partly preserve them? Or does it completely destroy these trivial K-cuts? As we'll see in a moment, these trivial K-cuts are actually partially preserved. Okay, but to formally define this partially preserved K-cut, we need to introduce the most important definition of our paper, which is going to be at the heart of all of our future discussions. Okay, so it's the definition of what we call border and islands, and hopefully this definition will be intuitive or gets more intuitive as the talk goes on. So it says the following: given a K-cut C with exactly R singleton components, we're going to denote the singleton components V1 to VR, and the other components, there's K minus R of them, as SR plus 1 to SK. A border of C is a cut obtained by merging some singleton components into the other larger components. And don't worry, there will be a diagram coming up real soon. So more precisely, a border is defined by a subset I of the singletons, and intuitively, we should think of I as the set of islands, okay, and a function sigma that's going to map the islands to the larger components SR plus 1 to SK. Okay, now given the set of islands and this map, we are going to define a new large component as follows. We're going to say SI prime is SI, which is the original large component, union all the islands that is mapped to SI. Okay, so now how many components do we have? We have a total of K minus I components, and the border BI sigma is just a K minus I cut defined by these components. So the new large components, which is K minus R of them, and the other singletons that was unmerged in the process. Okay, and we call the set I the islands, and this BI sigma we call the border. So let me try to make sense of this definition with a diagram. Okay, so here's a diagram of a K-cut. There's a total of 7 large components and 8 singletons. Okay, and in this, so the singletons are both the yellow dots and the black dots. And one particular border that we can define is we identify these yellow dots as this island, and then we're going to merge them into the large components that are drawn here, that are drawn to include them. So in particular, the resulting border that we're going to get is a 10 cut, because we merged 5 singletons into the large components. And the border is just seen by these blue lines and the black dots, which are the singletons that are unmerged. Okay, so hopefully this diagram provides a little bit of intuition onto this definition. But the natural question to ask is, well, there are so many ways one can define border and islands. Why do we have to do it this way? Why do we have to select a subset of islands and then discuss like the map from islands to like the larger components, which we're going to conveniently call continents? Like, why do we have to make the definition this way? Well, it turns out that if we modify the KT specification for K-cuts for just a little bit, we can get the following result, which says, given the graph G, we can compute a partition as usual, and every minimum K-cut, trivial or not, but we're going to consider trivial K-cuts, have at least one border, BI sigma, preserved in the resulting multigraph H. Okay, so this is what we mean by every trivial min cut is partly preserved in H. Moreover, H has the same number of vertices as before, and we get a very nice bound on the sides of the borders. And this is kind of what you expect, because the borders are now just K minus I cuts. So it has the proportional size. It's K minus I over K times lambda K. Okay? So this is quite amazing. Now, the natural question to ask next is, how do we find these preserved borders? It turns out that we can just apply the Karger-Stein algorithm. So as shown in GHLL, which is the new analysis of the Karger-Stein algorithm, we have the following law. It says fix an integer s and a parameter beta. and consider an S cut C, so think of this C as our border, bi sigma, of size at most beta of lambda k. Then there's an n to the beta k time algorithm that computes a list of cuts such that the border is one of them. Okay, so it includes the border. So this is quite amazing. We're going to apply this lemma onto graph H, and the overall runtime is going to be n over lambda k of k minus I over k times k. Okay, because recall that our graph H has n over lambda k vertices, and from the previous KT sparsification result, we have a bound on the sides of these borders. Okay, so this is quite amazing. This is actually faster than n to the k. Now, this will locate the borders that is being preserved in H. The next natural step is just to find the islands which is lost in different continents, right? Because we have these islands merged into different continents. We don't know how many is merged in which continents, but we need to find them. And the important observation to make here is that the finding islands in each continent is independent because the continents are completely cut off by the border. So it suffices for us to just consider each continent separately, right? And we consider just the following problem. We call it R island problem. So given a graph G, think of this as a large component. Okay, we need to find the optimal R plus 1 cut C, which has exactly R components, R singleton components, right? So we're basically taking a large component, which we guess has a total of R islands, and we're just going to locate those R islands by running such a cut algorithm or studying such a cut problem. Now, it shouldn't be surprising that a modified k-clique algorithm using matrix multiplication would suffice. Oh, and I just realized I never introduced omega. Omega is the matrix multiplication factor, and last time I checked, its omega is less than 2.373. So apologies for introducing it this late, but the modified k-clique algorithm is just going to make use of matrix multiplication. And the lemma that we have is that there's an n to the omega r over 3 deterministic algorithm that solves the R island problem. Okay? So now let's put everything together. Our main algorithm basically go as follows. We run an approximation algorithm first to estimate lambda k. If the estimate is small, less than n to the 1 over t plus 1, we run the exact algorithm by LSS. Otherwise, we apply the KT sparsification to obtain graph H on this many vertices, because now lambda k is large. And then we guess, or we iterate over all possible value of I, which is the number of islands, because we don't know how many of them, but there's at most k possibilities, so this doesn't blow up our runtime. We're going to run Karger-Stein to obtain a set of cuts that is going to contain my border. And for each cut C, we're going to guess the number of islands in each continent of C, because we don't know how many of them there are. And we're going to run the island discovery algorithm for each continent. And in the end, when this procedure is applied on my border, it's going to return my minimum cut, okay, if I have the right guess. And this concludes our algorithm. If we put all the runtime together, we see that we get the promised results right here, which with this constant C, we can have a minimum cut algorithm that runs in time n to the ck. Thank you. This is the end of my talk.